This video will hopefully clarify the difference between percentage discrepancy and percentage uncertainty, and how we use percentage uncertainty as a cutoff to see if our percentage discrepancy is acceptable or not. So here I have some mock data, and I've worked out the final answer. I've made up some random reference value that we can use to compare. And so we go through our discrepancy calculation, and we finally end up with 14.4%. So is this good? Is this bad? At first glance, it might seem that you're pretty far off, 14 being bigger than 10%, say. But there's nothing special about 10%. Rather, you should really base that cutoff on your actual data. And to explain that, I like to use an analogy of, say, hitting a target. So here I have a target, and the middle of the target is basically our reference value. That's the target we want to hit. We want our experimental value to be exactly dead on to the reference value. This is, however, often not the case, so we hit somewhere off to the side, which is our experimental value. Then we ask ourselves, did we hit the target? Did we miss the target? The distance where we hit our experimental value and where we want to be, the reference value, that's our percentage discrepancy, which is a measurement of how far you are away from the reference value. Now, is that big or is that small? That's when we have to think about, okay, since our incoming data has uncertainty, our answer also has some amount of uncertainty. So let's look at this uncertainty thing. You can have an answer or experimental value that's very, very well defined and small, so it's like a needle point. Or you can have a final result that has quite a bit of uncertainty. It's quite fuzzy around the edges. We have a huge range. So the pinpoint is a low uncertainty. Some people call it high precision. Like, you know that number to many, many decimal places. You have very little uncertainty. Or you could have a fuzzy, high uncertainty situation like we have on the right, which we call low precision. So it's more like a scatter shot. It's huge range. And as a measurement of how fuzzy things are, we use this percentage uncertainty, which is how fuzzy your experimental value is. Well, how does this combine with our percentage discrepancy? Well, let's put that on to our target. So instead of a fine pinpoint, we have that fuzzy scatter shot of a fairly large percentage uncertainty. So you have your, again, percentage discrepancy and your percentage uncertainty. Now, being such a fuzzy, big scatter place, you can actually see that the fuzziness actually includes your target. So in that sense, your answer could be right, given that you're covering such a huge range. So this is the case where you have your percentage discrepancy is less than your percentage uncertainty. So your percentage uncertainty actually covers that difference. Because you're so fuzzy, it's not surprising that you're as far off as you are. In that sense, we will say then the experimental value agrees with the reference value. That's the keyword we use, agrees. By contrast, if we replace that same point with a very precise, fine point that we know very, very well, very low uncertainty, then we know for sure we missed, right? There's no chance that can overlap anywhere to our actual target. So this is the case where your percentage discrepancy is bigger than your percentage uncertainty, and so the results disagree with the reference value. You know for sure that they cannot be the same as each other. Now, of course, in the ideal case, you want a very precise, fine point that is on your target. But I'm just showing you how the percentage discrepancy, the cutoff of it, is your percentage uncertainty. Going back to our actual example with all these numbers, how do we figure out the actual numerical cutoff? Well, in this course, as a simplicity, we simply go back to our raw data and look at and find the largest percentage uncertainty in the raw data. Percentage uncertainty is calculated using the uncertainty dividing by the number times 100% to make it into a percentage uncertainty. The units always cancel out, and you have your uncertainty on top, your value underneath, and you get a certain percentage. And you do that for all your values. And then again, to simplify things, we simply just pick the biggest one. We don't add them up or anything, we just pick the biggest one. And in this case, the biggest one is the 21%. So then this becomes our cutoff, whether or not we're acceptable or not. So in this case, 14.4% is less than 21%, meaning our percentage discrepancy is less than our largest percentage uncertainty. As we saw from before, that means we have a fairly large fuzzy scattershot, part of which overlaps with the target, so we can say that the experimental value agrees with the reference value. So hopefully this clears things up about what we mean by using your percentage uncertainty to see if your percentage discrepancy is acceptable or not.